So hello everyone, myself Malay Mahajan. I'm a second year student here studying maths and computer science. And in my high school I also prepared for maths and Olympiads. I was a 3-time awardee from 22 to 24. Okay, so today we will be giving a joint talk. The first part will be given by me and the second part will be given by Shyam. So if in general if you have any questions at any point of time, feel free to interrupt and just straight up ask the question. And and if any definition or something is not clear, just tell, and I'll try to make it as interactive as I can. And in case I ask a question and if you know the answer from before, and don't try to spoil it immediately. Okay, so today we'll be learning about constructible numbers. So I'll explain the setup. So what we are given is an infinite ruler. So it's a straight edge. Straight edge means it's an infinite ruler, but you don't have markings. As in, you cannot say this is length 2, this is length 1.5 something. You just have, and it's infinite on both sides. Straight edge and a compass, and you are marked unit length. Say, just like I come and tell you I give you this segment and I say this has length 1, and well, you can do perform the usual operations. Operations as in, like, you can intersect two lines, you can intersect two circles, I can mark a point in the plane and everything. So, and the question is, what all numbers can you construct using this? So is the question clear to everyone? No doubts with this? Yeah, so this is one of the questions we want to answer, and we also want to we'll address a question in the other way, as in, is there something we can't do? So the title is about trisecting an angle, which we will see if we can do it or we can't do it. So let's get started. So is there any initial observation, something very basic, given a length 1, can we do anything else? You can get all integers, right? So you have 1, I can just add one more 1 here, just take a compass and just make this a line. Take a compass here, reflect, and I get 1 more, and this length is going to be 2. So I can do 2, and similarly I can repeat and I can get all natural numbers. And okay, so one more thing I'll be using is so obviously we want to construct lengths, and lengths by definition are non-negative, but I say you can do -n, like say I will say I can do -1. We just say it as in, like I don't mean distance -1, but like what I mean is, say I'm given a length x, and if I want to construct x -1, I can do that because I can cut off 1 from here, and this will now be x -1. So I call this -1. You can think of it as -1 in the other direction. So do you see why you can do all of integers? Just 1 in the other direction. You can think of it like that. Don't worry too much about the negative sign. So this is clear. Is there anything else you can do? So the first thing you can do is Z. Sorry? Is there any other idea that you have? Rationals. How will you get to rationals? Yes. And okay, so to start off, for example, you can bisect a segment. So I can get to half. You can bisect using, I'm sure you would have seen in high school geometry, just bisecting. So you can get half, and you also want to get 1/3, 1/4, and other things. And how you get that is using similar triangles. So okay, we'll make this claim: A constructible implies 1/A constructible. By the way, should I write? Can anyone read this? Yeah. Obviously, as you may, is non-zero. So how you do this is as someone pointed out, we use similar triangles. So we are given a length A and we are marked 1. So just mark 1 here and we just make this triangle. And I can also mark 1 here. And I draw a line parallel. I can draw a line parallel to this. Yeah, has everyone seen that you can draw, given a line and a point, you can draw a line through it which is parallel to this using our compass and keys. Has everyone seen this? Yeah, so you draw a line parallel and so this is 1. Now what will this be? If you call this x by similarity x by 1, which is this by this, will be 1 by a. Is this clear? X by 1 will be 1 by a. So x is 1 by a. And this length which I have constructed is 1 by a. So that's clear? So you have this and now, so you can do integers, so you can do all of, 1 by 2, 1 by 3 and everything. And so in general, I'll make one more observation. Suppose you can construct AB are constructible. Then given AB, what all can you construct? Sorry?
A plus B.
Yes, you can do A plus B. Just put it, okay, so to be very, so you have A and you have B here. So you can make a parallelogram and you can translate and you can put it along the same line and this B. This is fine, right? Because you can draw parallels, you can translate this length from here to here, even though it's not parallel, but you can translate it from here and then intersect with this and make it as. So this is clear? So even if you are not given them along this, you can translate by parallelograms and drawing parallel lines. So you can construct A plus B and similarly you can do A minus B just in the other direction as I pointed out. And yeah, is there anything else that we can do?
A times B.
You can do A times B. You can do A by B, follows from this observation. So, and okay, so we have all of these things that can be done. Now, is there anything else that we can do? Maybe something more?
Root of it. Root square root.
Yes. So one thing that we will get to is, so this is one of and the last observation we will make is root 2, root 3, all of them are constructible. And how do you construct this? Yes. So how you construct this, I'll get to this side. So for root 2, you take 1, you draw a perpendicular line. How you just make this an infinite line and just take a perpendicular, mark length 1 here, and by Pythagoras theorem this is root 2. And similarly, you can take 2, 1 and this will be root 3 and you can repeat this. So okay, so now what we have is, you can, given, say at some point you have constructed some numbers, what you can do is close them under addition, subtraction, multiplication, division and square roots. Square roots, in this case we are taking root 2, root 3 and everything. So is everything clear so far? Yeah? And I'll now get to the first definition of today's talk, which is, okay, other than this, which is what a field is. So for the talk I only require fields which are subfields of C. So in our setting, I'll define a field which is subfield of C. C is complex numbers, okay? So we'll be only dealing with this, and F is called a field if 0, 1 belongs to F and it has exactly this property. AB belong to F and implies A plus minus B, AB A by B belongs to F. Here I assume be non-zero. So this is the definition. It is like, it's just a structure where you are given 0 and 1. You can add, you can multiply, you can subtract, and you can divide by non-zero numbers. So is this clear? And so what are some examples of field? Remember, we are now only going to take subfields of C. So you don't have to, like, whatever example we take, we'll only do in this reference. So what are some examples? Sorry? Yes. So okay, the start of the most obvious field is first C. So obviously it satisfies this property. As you pointed out, reals also form a field. You can check all of these axioms. Rationals also form a field. Is there any other field that you can give?
You can join any rational.
Right. So we will give one more field, which is so suppose you have some number alpha. You have a number alpha which belongs to C. It's a complex number. I'll define what the field generated by Q comma alpha is, and this will be given by. Okay, so you want to form a field which is generated by Q and alpha, and how do we do this? When I say field generated by Q and alpha, you kind of want like the smallest field which contains Q and alpha. So say I want alpha to be there and Q to be there. What all elements are forced to be there? As in, okay, alpha should be there. Should alpha plus 1 be there in the field?
Alpha plus x for any x belongs to Q. Alpha
Yes.
plus x.
So because of these properties, alpha should be there. So alpha plus 1 should be there, alpha plus 2 should be there. Alpha plus 1, alpha plus 2, rather alpha plus any rational r should be there. Just put like something 3 by 4. Then something like 7 by 5 alpha. Should this be there?
Yeah.
Should be there because of this, right? We can divide. In particular, will alpha square be there? Because I require alpha to be there, and because of these properties I should be able to multiply. So alpha square should be there. Now alpha cube should also be there. Now, like, do you think alpha cube plus 5 alpha square plus 1 by 2, should this element be there?
Yeah.
Because alpha cube should be there, 5 alpha square should be there, half should be there, and I can add. So in general, if I generalize this, what do you think? What all elements am I forced to put?
All polynomials with rational coefficients.
Not polynomials, but polynomials evaluated at alpha. So rather you take all polynomials which belong to Q of x. So this notation refers to all polynomials with coefficients in Q and variable is x. This is clear, right? And you take P evaluated at alpha. So all of these should be there. This is clear, right? Because polynomial evaluated at alpha is just like some combination of combination of these things which should be there. So does everyone see why all of these things should be there in the field? Now if you just take the set P alpha varying over P, what all have we included? We have included this, because polynomials multiply to polynomials. But have we included inverses? As in, just take alpha. Do we know something which is 1 by alpha a priori? We don't. So we have to add 1 by alpha, right? So we have to add 1 by alpha. You have to add 1 by alpha square. You have to add 1 by alpha plus 2. Why do you have to add 1 by alpha plus 2? Because alpha plus 2 is an element here. I want an inverse. So if I generalize this, what will I get? You will get 1 by polynomial, right? Let's say any polynomial, I should have an inverse, which is 1 by P alpha. Remember, everything is in subfield. All of these numbers are complex numbers. So this should be there. So in general,
We can have any P alpha by Q alpha.
exactly. So we must have P of alpha by Q of alpha. As in, okay, I just replace this with Q, and their product should be there. So this is there. So in general, or these are called rational functions. If you have, so we know that all of these should be there as you vary P and Q in this. And does this set form a field? As in, I claim field generated by this is and provided G of alpha is non-zero. You can check that this forms a field. I mean, any two if you have any two things of this type, you add, you still get a polynomial in the numerator, denominator is still a polynomial, which is a product. Evaluate alpha, it's still something of this type. And inverses is all fine because you just take it. So is this clear? So yeah, this is one thing that we will be using later. Shyam will get to more about this. And so for example, we'll also need something like Q root 2. It's kind of like the field containing Q and root 2, and you can check that. So okay, because root 2 squared is 2, I only have to consider polynomials of degree at most 1, right? Because if you take a polynomial of degree 2, its x squared will give 2, so you don't have to add it. If you take polynomials of degree 1, it's all be covered. So you will have a root 2 plus b, where a, b belong to q. And Shyam will most probably get to this. You don't have to add the denominator. You can check that you don't have to add the denominator, because in this case you can actually just work it out, and given something which is like c root 2 plus d, you can actually find an inverse here. So it so happens that this forms a field. Okay? So this, and so q root 2 comma root 3, this will be generated by c root 6 plus d, where a, b, c, d belong to q. So is this fine so far? I mean, I have not explained this to you, but just believe me, and this is the case, okay? We won't just, this was just to give some examples of field, and we will need a bit of this later. So everything clear so far? And now the next topic, the next thing we will come to is, so we have, the definition of field is clear, and observe, what does this observation infer? What can we say because of this observation, from this observation? Yes, the form of field. Yeah, so that's good, and this was the reason why I defined what a field is. And now, field operations only have these things. This is already there in a field, because you have 0 and 1 is there. You have this. This is already there in a field. So this I have added, this I have added, this I have added. What is the only other observation we had?
Square root.
Square roots. And that is not guaranteed in this, right? As in, for example, fourth root of 2 is not there in this field. But this is some extra property we have about constructible numbers. So can you replace this with something? As in, can we get a stronger remark rather than just saying this? And so the remark what the claim we have is C constructible implies square root C is also constructible. Just assume C is positive. And okay, I'll just quickly tell the proof. The proof is, you take 1 and you mark C here. Remember, C is given to be constructible to me. What you do is, so you take the midpoint of 1 plus C, and I can mark a circle with this as the diameter. Is this clear? And now I drop a perpendicular through this, and this length is 1, this length is C. Well, because this is a diameter, this angle has to be 90, right?
This length is root C.
And now what is this length?
Root C.
So I hope everyone knows that if you take a triangle and drop the perpendicular, if this is x, this is y, this is z, then x squared is yz. This squared is this times this thing is z. You would have seen this in high school. So x is literally root c, because this is 1 and c. So the claim is proven. So everything clear so far?
Yes.
So okay, what we have seen is they form a field and you can also close it under taking square root of something you have. And now the question is there any other operation that we can do? So I'll erase this. So do you think we can do any other operation? And the answer is no. So what we have done so far is we showed that all of Q can be constructed. And after that, what did we do? This one step that we did went to Q, comma. By the way, this is denoted by definition as this. Okay. So if I use Q bracket alpha, it means the field generated by Q and alpha. So what I did is I can attach a root C for C belongs to Q, C greater than 0. So this is the one operation that I can do. And did I ever use that C is a rational number here? No, right? So if I have constructed a field F at some point, what I can do is I can get F root C for C belongs to F, C bigger than 0. Is this observation clear? Because I'm never using that C is rational there. So this is one operation where F is a field, and you can think of it like an iterative process. You start with Q, you attach say Q root 2, then you attach something more. Like then I have the liberty to attach fourth root of 2, because given root 2 I can construct a root of root 2. So you can think of it like this, and because of the one observation I had, if you have A and B are constructible at any point, I can add addition, multiplication, all of them is there. So I can close it under a field. So is this clear? Your F stands for a field. So this is the one operation we have, and well, what I will prove just now, I'll prove now is you cannot do anything more. Okay, so can we do anything else? And the answer is no. So let us go back to the definition which I just erased. But in the definition, so what all operations can we do? How do we generate a new point, or how do we generate some new distance? So given what can we do, as in you can take a line from 2 points. The two operations we have are, given points x comma y in the field F which we have so far, make a line through x and y. This is denoted as, okay, I should not write this, I'll write x naught and y naught. This has equation y equals mx plus c, where m and c belong to the field F. You can just check this, as in you can get the exact equation of line. So this will be t x naught plus 1 minus t y naught, and you can check that they lie here. This is the first thing. And what's the circle? You can draw a circle x naught, y naught are belong to F. Then you can make the circle, you can draw the circle with this equation. Right? So these are the only two things we can do. And if you look, if you want to introduce a new point, it has to come from intersection of either two lines, or intersection of a circle and a line, or intersection of two circles. Okay. So now let us look at. By the way, if you don't want to think of Q, you can start with Q. I can replace this with Q, and the exact same thing goes through for F, but we will need to use F at some point. So if you are slightly confused now, you can think of F as Q. And now, okay, so what are the three things we can do? So we can take intersection of two lines, intersection of a circle and a line, and intersection of two circles. So in terms of nature of F, what can you say about the intersection of these two, a circle line or two circles? What can you say about how will the intersection look? it's not exactly this. I mean, okay, what do you mean? As in, okay, it might be good if I replace this with Q. Just say, okay, just suppose I only have Q right now. I don't have anything else. Now, how will the intersections look like?
We don't have that quadratic formula.
Exactly.
That.
Yes, and that's the answer, and I'll come to it now. So suppose, what I claim is, say you have this line which is y equals m1x plus c1 and y equals m2x plus c2. These are the two lines, and suppose they have intersection point. This is a circle which is x minus a1 squared plus x plus y minus b1 squared equals r1 squared, and the line is y equals m1x plus c1, where here all of these constants m1, c1, m2, c2, a1, b1, r1, all of them belong to q, because I'm assuming you only have points through q and this thing, and here you have equations of two circles. I won't write it again. The intersection points reduces to solving system of two equations, at most quadratic. Right? Both of them are at most quadratic. So if you just solve them, you won't have anything outside a square root. Is this clear? I mean, here you only end up with q. You don't have to leave the field. Just solving a system of equations, and the worst thing you have to add is a root 2. I mean, by quadratic formula you will have some minus b plus square root b square minus 4ac by 2a, but the minus b and minus 2a you can get rid of because you are working over a field. Yeah?
In this particular case, I should say by x2, because for two circles I can just subtract them and get rid of the x square term. But in general, this is true. I mean, why can't I have a system of quadratic equations and the solution is not representable in quadratic terms? I don't know.
You can just check this, as in you subtract.
Yeah, in this case, I'm saying you are solving a system of.
I'm only referring to this. In this case, when you solve it, you will end up with at most this.
Okay.
And so, if x and y, the intersections, they will belong to q root e for some e, that should not be easy, for some alpha in q bigger than 0, right? Is this clear? The worst you have to add is a square root. So, is this observation clear? And remember, solving a system or a field, I can now replace all of this with an f. I can put this f, these equations, I'll just replace this with f. So given something with f, the only operation I can do is I can go to f root alpha for some alpha which is there in f. So is this point clear? And now I'll come to kind of like the formal definition of a constructible number. Alpha belongs to C is constructible if, so remember I said this, you can think of it like an iterative process. You do one step after the other. So there must be a step, for example for square root 2 you just do one times. For square root 4 you repeat it 2 times. So there exists a sequence alpha 1 all the way up to alpha n, all of them are belong to C, such that alpha, the number you want to construct, belongs to q square root alpha 1 all the way up to square root alpha n. So at the end I have added these roots and alpha belongs there. But I need one more condition, right? As in I need these numbers to be constructible from the ones I know before. Say for example I start with root alpha 1. Alpha 1 suppose is 2, I have added root 2. But in order to add square root alpha 2, I need this thing to be satisfied. So what that equation will be means for all I, alpha I belongs to q square root alpha 1 all the way up to square root alpha I minus 1. At step 0 this means alpha 1 belongs to q. So I'm adding an element, I'm adding a square root of a rational, At the next step, I have q and q square root alpha 1. I can add an element of I can add root of an element which is there here, and I can repeat the procedure, and that is all I can do. So is the definition clear from this observation?
This is just this written form.
Exactly. It's just, this is one, it's two ways. I can do this, and conversely, this is the only thing I can do. So it's a if and only if, and hence the definition. Definitions are always if and only if. So is this definition clear?
I will be taking alpha into the complex and using these operations, I can never escape real numbers.
Sure, you can, yeah, you can, I mean, yeah, so you won't leave real, sir. You can think of everything as real, yeah. Yeah, perhaps it might have been better to just do this, but yeah. Yeah, and now Shyam will continue on this.
Right. So the second half of the talk, well, it might get a little technical, but yeah, just bear with me. So, well, first of all, we ought to appreciate the definition of constructibility. I personally find it very beautiful, in the sense that, I mean, you see, in hindsight, this is obvious. You are iteratively attaching square roots, and that's all you can do. And something is constructible if it lies at the end of such a tower, whatever field you obtain at the end. But, right, and okay, we will see how this abstraction has it. So, okay, we are going to reap the benefits of this abstraction. Right, let's just write it. Okay, this is something I will want. Right, this is something I will want. So, right. So I want to define, okay, so, right, so once we have abstracted the definition of constructibility, now, in some sense, the geometry is out of the picture, and now we are doing algebra. And, in fact, okay, so we are doing field theory. One of the first definitions in field theory that you will see is that of degree. And right, okay, so no, I just need to, sorry, I'm just finding a good launch pad to kick this off, but fine. So I will make one further assumption on the alpha here, which is that alpha satisfies a polynomial equation. This is not always the case, in the sense, for instance, if alpha was pi, we all know pi to be transcendent. What this means is pi does not satisfy a polynomial equation with coefficients in Q, right? However, I will assume that all the alphas that we take, they will all satisfy polynomial equations with coefficients in Q. And in fact, that will be the case because, for instance, at the first step of our tower, alpha 1, okay, what polynomial equation does it satisfy? Sorry, what does root alpha 1 satisfy?
X square is equal to alpha.
Exactly. So it satisfies x square minus alpha 1 equal to 0. What does root alpha 2 satisfy? X square minus alpha 2 equal to 0. Where now this alpha 2 is an element of the field generated by Q and root alpha. Right. So, right. So, okay, what we do is we will see if time permits why we can do this, but anyway, right. So okay, if alpha satisfies some polynomial equation f alpha, you can look at the f with minimum degree, so that has alpha as a root. We call that the minimal polynomial of alpha. So by the way, such alphas which satisfy some polynomial equation are known as algebraic. So alpha, the minimal polynomial of alpha over q. I know this is not getting sympathetic, but this is defined to be f of smallest degree. See, right. This is the definition of the minimal polynomial, and I will define the degree of alpha to be, well, the degree of the minimal polynomial. Okay. Right. I hope these definitions are fine so far. So, in fact, okay, this is what I define to be the degree of alpha. I will also define this to be the degree of q alpha over q. Right, so I am using this, the degree of the minimal polynomial of alpha, to simultaneously be the degree of alpha itself as well as the degree of the field q alpha over q. Right, and so okay, so okay, there is one more thing that I will black box for the moment, but I really want to prove this because I want to leave you with some amount of rigorous mathematics by the end of this talk, which is, so when alpha is algebraic, that is when alpha satisfies some polynomial equation here with coefficients in q, we have that q alpha is really how does this differ from this? With coefficients in
Modeling out by the
sorry.
you are modeling out by the minimal polynomial.
True, but I mean just stare it. Okay, suppose I were to make this a definition. How does this differ from this definition? You see, there is something missing. Exactly, you are missing all the denominators here. Right, you see, what I am saying is when alpha is algebraic, that is, it satisfies this thing, you don't really need to introduce denominators. They are already there as polynomials in alpha. This is something I would like to and should I just prove it? Fine, yeah, I'll just I'll just prove this. So okay, just symbolically, all polynomials in alpha with coefficients in q you write as q square bracket alpha, and q round bracket alpha is all the rational functions in alpha, which is polynomial in alpha divided by polynomial in alpha. Right. Right. So okay. So proof, well, stripped of all details rather. The idea is this. So okay, alpha being algebraic, it has a minimal polynomial. Right. It has to have a polynomial of smallest degree that satisfies. So suppose call it f. Right. And suppose you are given some okay, we've used f there, so let's call this p. So what you want to say is, given an expression of the form f alpha times f alpha by g alpha, you have 1 by g alpha already in the field, right? So, right. So, okay. I claim that. So the G here. Given G alpha not equal to 0, the GCD of P and G as polynomials is 1. They are coprime. Why is this the case? Because in polynomial rings you have division with remainder, right? So, and P is monic, so you can divide G by P to get a remainder, right? And this is your Euclidean algorithm. So therefore the GCD of P and G must be 1. Is that fine with everyone? But now the moment you have the GCD being 1, you have base 2, which allows you to express 1 as a polynomial combination of P and G, right? I hope everyone is following this. So you have P times some H plus G times some H1 times H2 is equal to 1. And now put plug in alpha. This term is going to die because P is the minimal polynomial. What you get is G of alpha times H2 alpha is 1. And therefore 1 by G alpha is, which is already in your polynomial. Right? So you see, nothing is lost assuming that nothing is lost removing all the denominators, because the denominators are already expressible as polynomials. The reason I did this was, well, so okay, so this is how you can define the degree of some an extension where you are just join one element, where you are just attach one element outside as the degree of the minimal polynomial of that attached element. I now want to generalize this. So right. So okay, right. So you see, having done this, now what does Q round bracket alpha look like? So Q round bracket alpha is the polynomial ring in one variable over alpha over Q. Sorry, it's a polynomial ring. It's the it's all polynomials in alpha with coefficients in Q. Right. What do elements of this thing look like? Yes.
How do you show non-trivial inequality codes? Like you show that all these polynomials will exist. But how do you show it will never happen that there will be two polynomials that actually just same?
No, that could happen. In fact, okay, exercise. If two polynomials, when you evaluate at alpha, are the same, their difference when evaluated at alpha is 0.
Yeah.
Right? This implies that the minimal polynomial divides their difference. Do you see that? Take it as an exercise. Okay. The minimal polynomial really is the minimal polynomial with that satisfies that it's really the minimal polynomial which is satisfied by alpha. In the sense, if any other polynomial has alpha as a root, that polynomial will be divisible by the minimal polynomial. This is an exercise. This follows with a little bit of work from the definition. Right? So, right, but okay, this is in fact element. So, what do elements of this thing look like? Well, as a set, it's going to be, things of the form what? Summation Ci alpha to the I going from 0 to a. Ci in Q. These are actions, right? Well, so suppose this is some degree d. Do I need to go? You see, I don't need to go beyond d, because alpha satisfies a polynomial of degree d. So monic polynomial in fact. So alpha to the d is expressible as a linear combination of 1 alpha square all the way up to alpha to the d minus 1. But now I multiply this thing by alpha. So alpha to the d plus 1 is also expressible as a linear combination of alpha square all the way up to alpha to the d. And now I again express alpha to the d as a linear combination of 1 alpha square all the way up to alpha to the d minus 1. All in all, I don't need to go beyond d. You see, so this is really the set of all. I am going from 0 to d minus 2. The moment you hit d or higher, you can always express it as a linear combination of lower polynomials, right? Such that this is how we are going to generalize the degree. The idea is you treat 1 alpha, alpha square all the way up to alpha to the d minus 1 as generating this thing. Generating in what sense? Every element of this is going to be a linear combination of 1 alpha, alpha square all the way up to alpha to the d minus 1, where your permissible coefficients must come from Q. Does this make sense? So, really what you're saying is degree is of minimal generating set over Q, specifically over Q. Because you see, when you allow linear combinations where coefficients only come from Q, you cannot say alpha square is generated by alpha. It is algebraically generated by alpha as the square of alpha. But over Q, you don't have alpha square as a linear combination of, say alpha. You see? So we generalize this as, we generalize this to the degree being the cardinality of the minimal generating set over Q. The over Q is indicating that the coefficients come from Q. Did we use Q anywhere here? Not really, right? So you see, this definition is more general in that it makes sense for any fields, right? So, I hope all of you are following it, not just nodding your heads. So, okay. So, right, definition. So, given fields E and F, the degree of E over F, which I write as, which is, okay, this is not standard notation. Standard notation is this. This is defined to be with of a minimal generating set for E over F. For example, okay, let's just look at concrete here. What is the degree of Q root 2 over Q? And the one possible generating set is 1 comma root. Okay, what about Q? Say, okay. The golden ratio. Sorry. No. Someone said.
The degree is two.
The degree is 2. One second. Why?
It's a root of a quadratic equation. So
Exactly. So okay. So you are using this definition, which we have seen just turns out to be equivalent to this.
yes.
And the reason we chose this as the definition is because this is amenable to generalization. Right. So this is again 2. What about, so okay, what should the degree of this be over Q?
It's three.
And the generating set is?
1 to root 2 root 3.
Just, okay, stare at the expression.
Root 6, root 6.
No, we can't take Q.
1 root 3.
Yeah, 1 root 3 root 6.
You also need root 6.
Yeah.
Because root 6 is, sure, root 2 times root 3.
Yes, the
But if you want the coefficients to come from the rationals, you need to additionally add this. You need to attach the root 6 as well. You see? So this is going to have degree 4 over Q. With the minimal generating set being 1, root 2, root 3, root 6. I say the, but really it's a. You could have several minimal generating sets. You of course now, without, now you could get into the technicalities of it and say, okay, this is well defined. If you have another minimal generating set, minimal in the sense it cannot be cut down further. You don't have a subset of it which also generates. Right? You have to prove well definedness, you see. It's not entirely immediate why this is the case, why this is well defined. For those of you who know linear algebra, this is just the dimension of E as a vector space over F. And so the dimension is very defined. Right? How many of you have seen linear algebra to some capacity? Brilliant. Brilliant. So right. This is dimension of E and F vector space. For those who right. So okay, why did we? What is the fuss about degree? The nice thing is the degree is. Anyone want to finish the sentence? Sorry. The degree here will be a power of. Right. Right. The degree is multiplicative. That's what I want. Right. So okay, I'll just give an informal proof. Degree is multiplicative. Suppose you have fields K over E over A. Then the degree of K over F is the product of degrees of K over E and E over F. Proof? So you take a minimal generating set for E over F. Call it alpha I. This is minimal generating set for E over F. You take beta K to be again a minimal generating set for K over E. And the minimal generating set for K over F will be. Any guesses? Just this seems, if this seems suggestive at all. Not Cartesian, you literally multiply them. Well, this implies that you take all pairwise products alpha I times beta j. This will be a generating set for K over. You can check this. Is this believable? Okay, let's just do this orally quickly. So you take an element of K, right? You can express it as a linear combination of the beta j's with coefficients in. I hope I'm not lost. Oh god, is it too small?
No, my eyes are closed.
Well, okay. So, I mean, okay, okay, fine, look at the field extension K over E. If, oh wow, thanks.
I was unable to see it clearly.
Right, so, okay, what does it mean for alpha I to be a minimal generating set for E over F? By definition, it means that every element of E can be written as a linear combination of the alpha i's with coefficients in F. So now, okay, do the same thing. You start with an element of K. You can express it as a linear combination of the beta j's with coefficients in E. And every coefficient can be expressed as a linear combination of the alpha i's with coefficients in. So you just substitute this into your expression. And therefore every element can be written as a linear combination of alpha I times beta j with coefficients in E. I hope this is fine. Right? Yeah, please don't just nod along.
Why is this why is it very limited? What is on alpha 1, beta 2, alpha 3?
Right. And I will conveniently circumvent this. There is work to be done here, you see, because to say that this is well defined, that itself requires work.
Do you need linear independence?
Yes, you do need linear independence. This is really speaking the definition of degree. It's the dimension of the overfield as a vector space over the underfield. Right. Dimension is well defined. Okay, for those of you who do know linear algebra, exercise proves this is linearly integrated. Take a linear combination, set it equal to 0, see what you get. Right? Wait, okay, can I have the hands up of everyone who has seen linear algebra before? Just so that I know where we stand. Brilliant, then I need not have, gone through all this rigmarole, I could have just defined it this way. But anyway, fine. If that is the case, fine. Well, then you just take this to be the definition, right? If you all know linear algebra. And just try making sense of this proof. So this proves spanning. You have to prove independence, right? But as a consequence of this multiplicativity, we have something very nice, which is the following. So you have alpha constructible implies you have which is sitting inside some extension where you have iteratively added square roots, right? Alpha 1, alpha 2, alpha 4, right? This itself you can realize as obtained by q root alpha 1, q root alpha 1 attach root alpha 2 and so, right? Now here we are in familiar territory. We will get away with this definition of degree. So okay, what is the degree of this extension? 2. Right? Minimal polynomial of this thing is x square minus alpha. What is the degree of this extension? No, I got a 2 and a 4. Make up 2. Sorry?
First to third is 4, second.
Right, first to third is 4. So okay, we are assuming that whatever new things we are adding, they are not already in our field. I mean, if you are intersecting two lines, the intersection is of course already going to lie in your field. So we are assuming here that whatever we are attaching are new elements, in the sense they are obtained by intersecting circles and lines or circles and circles. We will make that assumption. So this is again going to have degree 2, right? Because again root alpha 2 is going to satisfy x square minus alpha, right? This is again going to have degree 2 and so on. The point is you have this over q. What is the degree of this over q? Hit it with multiplicativity of degree.
2 power of
It's going to be a power of 2, right? Okay, fine. Yeah, 2 power in it. Right. I implicitly assumed that not all of these are additional elements, but for the sake of simplicity, yeah, we are only adding new elements. So this is going to be 2 to the n. Now, well, you can also use multiplicativity of degree to go down, you see. So what is the degree of q alpha over q? I mean just from here. Sorry?
Alpha is defined over like alpha 1 to alpha n only, like nothing else. So it will 2 power n. Like or like
So you see, this has degree 2 to the n.
yeah.
This is a sub extension. This is a sub less than, but you can say more.
2 to the k for some.
Yes. Point is, this is going to be 2 to the k for some. Right. So here you are using multiplicativity to go down.
Yeah.
Right. So the point is, this is going to be a power of 2. We have already observed by our naive definition of degree. By the way, I hope this is a quick sanity check. I hope everyone is comfortable with this transition in the definition. I mean, most of you have seen linear algebra. I expect most of you to. Right. So this is fine, right? Because you see what this says is the degree of the minimal polynomial of alpha must be a power of 2. Not 2 factorial, though it doesn't change anything. Right. No, I really want to emphasize this. Okay. And with this now we are ready to prove, impossibility of whatever angle trisection and this and that. You can't double the Q also, we will see this. Right. So, okay, we need one more ingredient here, which is, observe that so right, okay, the angle theta being constructible, what does this mean? This means I can, this means I can somehow get a measure of this. How do you measure this? Well, what we will do is, you take the point, you take the, what do you call this, the vertex of the angle, and you, what? Sorry, that was bad drawing. You take the vertex of the angle and draw a unit circle around it, centered at this thing. And now we have a concrete measure of this angle. You could draw the perpendicular here. And this is, so what is this going to be? Sine. Trigonometry enters the picture. This is going to be sine theta. This is going to be cos theta. Angle theta being constructible is, I am defining this to be cos theta being constructible. Just because, well, you want, some element of R. I mean, just making it precise what it means for an angle to be constructible. But you see, this in fact does the job, because if you can construct cos theta, can you recover the angle theta?
Yeah.
How?
We can construct cos theta, and if we can construct cos, we can construct sin theta.
We can draw
And it's one, so
We can also basically draw something rising here, like draw perpendicular and
Make a horizontal line of any particular length of cos theta. Oh, okay, length cos theta, fine. Sorry, just for psychological reasons, I am reducing the length of this
so we
segment.
can draw perpendicular
Huh.
on the x.
Of length?
Also like in then from other end we cut one.
Yeah, exactly, right. Exactly. So long as this is 1, so you have recovered theta from the length cos theta. You can recover the angle from the length of the cosine. Clumsy wording. But yeah, you get the idea, right? So this I take to be the definition. Now, okay, let's prove that cos 20 is not constructible. Yes.
How do we know that the converse is also like if we are not able to construct cos theta, then can we say that theta is also not constructible, because there might be some other thing which we can construct?
I am making this a definition, you see. I am saying the angle theta is constructible when the cosine is constructible. You see, if you can construct the angle in some way, you can always take the vertex of that angle, draw a unit circle centered at that vertex and drop a perpendicular. That is, you are allowed to do that by ruler and compass. And the length of, you see, the adjacent will be cos theta. So cos theta will be constructible. Right, I mean this goes two ways, right? Okay. If you can construct the angle theta, whatever be the length of, I mean, okay, these are rays, if you want to be pedantic. If you can construct the angle theta, you can, with this as the center, draw a unit circle and drop a perpendicular. And because this you are allowed to do with ruler and compass, this you are allowed to do with ruler and compass. So you get this length, you see. And so this is cos theta. Does that answer your question?
No, I thought that I was asking that this only proves that if theta is constructible, cos theta is constructible. But
Okay, but if you can get, if you have the length cos theta, why you can get the angle theta?
yes,
Is that fine, or is that your question?
that is also fine. I am asking if cos theta is not constructible, then how do we prove that theta is also not constructible?
So you see,
prove
this
the
was
opposite.
this was just motivation for the definition. When I make a definition here, I am calling an angle constructible if the cosine is constructible. I mean, if this is a definition, it also means if this not being constructible means by definition the cosine is not constructible. I just use this to motivate the definition. Is that fine? Right? So we'll show that cos of 20 degrees is not constructible. So right, any relation with a well-known angle here? 60. I mean, wait, okay, why? Sorry, fine. Sorry. Okay. Right, what is cos 3 theta? Someone just blurt it out.
4 cos theta minus 3 cos.
Is that for sine or cos?
Cos.
For sine, first is 3, then is 2.
Okay, what is it?
4 cos 3
4 cos theta minus 3 cos.
Right? So, you see, put theta equal to 20 degrees. What is cos 6? So we get half is equal to, okay, well, cos, fine, 4 cos cube 20 minus 3. So cos 20, it satisfies a polynomial equation with coefficients in Q. Right? So what can you say about, by the way, okay, so, right, fine. Satisfies what? 4x cube minus 3x minus half is equal to 0. Right? Or okay, fine, which is the same as 8x cube minus 6x minus 1 is equal to 0. This polynomial is irreducible. Right? And okay, just give me one reason why this is irreducible. Don't have to prove it, but just utter some name of something.
It's reducible as like rational root 3 and
Rational, right. Eisenstein doesn't quite work here because you require. Okay, Eisenstein mod what? You have a 1 here. The rational root theorem is, a short way of determining whether a polynomial over the rationals is irreducible or not. And this is, in fact, this is going to be irreducible. Right? What does this tell you about the degree of cos 20? The degree of the minimal polynomial. So really the minimal polynomial, in order that it be monic, you divide by the 8th root. But point is, this is 3. That's why this is not constructible. So yeah, that is the proof. There are a few more remarks to make here. Do I have the time to make?
Hopefully, yes, you can. You can go till 1:30.
Is everyone fine? Right, so okay. So okay, hence. Right. Right. What can I do? Suppose I don't need this. Okay, I don't need any of this. So by the same line of reasoning, another classical problem gets solved. Really, the idea is this: if something is constructible, then its degree over Q has to be a power of 2. Right? This also shows why you cannot say double the Q. What is the statement of the problem? You cannot double the Q. Don't repeat this statement.
Unit, then you want to find the cube of y the.
Right, given a cube of unit volume, can you find a cube that has double the volume? This is equivalent to constructing cube root. You see, if you had a cube that had double the volume, just take its length. That you can do. Right. So, okay. So this boils down to proving that cube root 2 is not constructible. What is the degree of cube root 2? It's 3 again. The minimal polynomial is going to be x cube minus 2. Here Eisenstein tells you that it is irreducible. So this is the minimal polynomial. Right. Okay. Why are minimal polynomials irreducible? Because the minimal polynomial is the polynomial of minimal degree having this as a root. If it factored, it would have to be a root of one of the factors, and that would have smaller degree. Right. So yeah. So So this is again not possible. Now, okay. So since we were talking about cosines, there is a natural question here. When is the regular n-gon constructed? Because you see, if you can construct a regular n-gon, you can get all these angles. And the angles of a regular n-gon are 2 pi by at least the what? Exterior angles. I mean, the angle inside is going to be pi minus 2 pi. Huh. So, but you see. Sorry, what am I saying? Yeah. The center angles that are 2 pi by. Sorry. Huh. So if you construct the regular n-gon, that is equivalent again to, you can recover its central angle. So that is equivalent to constructing 2 pi by. Right. So 2 pi by n, the angle, which is the same as constructing 2 pi by cos 2 pi by n. Right. When is this possible?
It is a power.
So do you have the answer?
Yeah, it is a power of 2.
Sure.
Like it can be done.
Right.
There might be something.
So this will answer given by Galois theory. So you see, this naturally leads to Galois theory. The answer given by Galois theory is if and only if n equals some 2 to the k times the product of pi's, where pi's are Fermat. 2 to the So, how do you get this? Okay, I suppose why did I write it? Sorry about this. How do you get this? Okay, one direction should be easy. One direction does not require Galois theory. It does not require Galois theory, though it requires knowledge of cyclotomic fields.
I don't know what that is.
Right. Okay, you can read it out. I suppose, yeah. For those who are interested. But I mean, okay, really, this belongs here. This belongs to I mean, this just fits in nicely with Galois theory, in the sense that you study this in the context of Galois theory, normally, at least when it's taught in courses. But yeah, nonetheless, you can read this. I'm sure there will be some elementary treatment of cyclotomic fields, especially for the Olympiads. Correct me if I'm wrong, but I believe there should be an elementary treatment of cyclotomic.
Like I've heard of cyclotomic.
Cyclopolynomials
Yes.
not reducible, but cyclotomic fields.
Cyclotomic field is splitting field of a cyclotomic
Yeah.
function, whatever that is. But yeah. So yeah, just read this out. Cyclotomic fields, polynomials, right? Whatever. Right. Also, I want to generalize this definition a little, because you see, I want to highlight the merits of Galois theory here. So Galois theory. So you see, I mean, okay, I come back to this. You abstracted out the definition of constructibility, and now you have field theory that answers this question. Something that you could not do using, Euclidean geometry or ruler and compass alone. I believe, so I just read this yesterday, but I believe that Hilbert's axioms are insufficient to answer this question because you have several models, blah blah blah, whatever it is. You know. Anyway, just look this up. There is an answer on Stack Exchange if you are interested. But yeah, the point is you can get a model where this is not possible, and I think when it is not possible to answer this question, I think in the same spirit as to why you don't have an answer to the continuum hypothesis. Why there is no. You see, is the cardinality of R the next smallest cardinality after countable? Right.
So yes, in Hilbert's axioms would uniquely define R square.
I don't know enough about this. This is just something I read. Look this up if you are interested on Stack Exchange. Yeah. So anyway, so this is another merit. So this is one merit of Galois theory, field theory. Another one is, let me generalize this definition a little, and I promise I will end with this. So you see, you called a number alpha constructible if okay. I'm going to recast this definition a little. So what it means for alpha to be constructible is, there exists a tower of fields starting with the rationals. Means there exists a tower of fields starting with the rationals Fn, which contains alpha, such that each Fi plus 1 is obtained by attaching a root from Fi, right, with alpha and F. Do you see why? So here the Fi's are just q root alpha 1 all the way up to root alpha I. This is what it means to iteratively attack square roots, and something being constructible means just it lies in some field that lies at the end of such a tower, right? Immediate generalization. Why stop at square roots? Why not attach n roots for arbitrary n? I mean, not just one common n, as n is 2 here for all these extensions. So, right. So alpha being okay, I'm just going to make an ad hoc definition here. Alpha being solvable by radicals implies means there exists a tower of fields of this sort where you are not attaching square roots but rather alpha I to the 1 by n with alpha I. Do you see where I am headed? Another classic result, celebrated result in mathematics, which is sorry. Yes, exactly. So for quadratic equations, you have the quadratic formula, cubic equations, cubic formula, quartic equations, quartic formula. Degree 5 and higher, you don't have a formula. They are said not to be solvable by radicals. What does it? I mean, they are said not to be solvable by radicals. What does it mean to be solvable by radicals? So you see, when you take something that is solvable by radicals. For instance, whatever 1 plus root 5 by 2 plus cube root 3 minus some of the expression. What it means for something of this sort to be solvable by radicals is, you start with cube. You first attach the square root of 5, that gives you this entire term. Right, that's the first step of your extension. You attach the square root of 5. Then you attach a cube root of 3, the second step of the extension. That gives you this plus this. 7 is already in cube. You can divide by it. But you can subtract it. You can divide by 8 because it is already in cube. So for something of this sort to be solvable by radicals precisely means this, that you again have an increasing tower of fields where you are attaching nth roots instead of square roots, as we do for constructibility. Right. So this is, for instance, solvable. Right. So well. So you have the will finish here. It says, so what does it mean for a polynomial not to be solvable by radicals? It means its roots are not solvable by radicals. Arbitrary polynomials of degree greater than 5 are not solvable by. So just because I made an ad hoc definition here, their roots are not solvable by radicals. And again, the proof that I know of is the Hilbert theory. Again, highlights the merits of the Hilbert theory. Okay, one historical remark. So, you see, Gauss, he is famously known to have constructed the 17 bond at the age of 17. And there is an ugly expression for the cosine of 2 pi by 17. It's a monstrosity of an expression. Well, 17 is a Fermat prime. It's 2 to the 2 to the 2 plus 1. Right? Galois theory tells you without having to lift a ruler or a compass that yeah, it's constructible. So I mean, not once in today's talk did we lift a ruler or compass or do any construction of any sort, except perhaps drawing a circle, intersecting it with a line, or drawing 2 circles and saying yeah, you have these points of intersection. But yeah. I suppose that is about it. We should discuss one. Sorry for going over that.